Hello, students. This is Mrs. Farrell. You don't know me. I'm just a disembodied voice to you, but I am a math teacher, so I'm here to help you with some hints on your Math 4 Unit 1, Lesson 1 honors questions. So here we go. So exponential models for growth. Here is given to you a function. And the function is P of W equals 10,000 over 1 plus 49 times 0.85 to the W. And the first question is asking you what number of ants does the model give for the start of the experiment? So hint number 1 says, remember that a function is an input-output relationship. So what is the input and what is the output? So trying to decipher in this scenario, what is your input that you're plugging into this equation and what is your output that you're getting out from the equation? So my hint to you is that one of them is W, number of weeks, and one of them is P, population of ants. So try to figure out which one's your input, what's your output. And hint number 2 down here says, what would the input be at the start of the experiment? So when you're starting the experiment, what is the number that you will be plugging into your input? And after you figure out what that is, then you just do your calculations and figure out what output you get from that input. Once you see it, you will see that you can easily figure out what that start of the experiment is by looking at the equation. Okay, so that is problem number 25A. So moving on, we have for problem 25B, the question is, what is the shape of the graph and what does that shape say about the pattern of increase in the ant population? So your hint is to graph the function in your graphing calculator. And your graphing calculator doesn't like W's and P's, so you need to use X and Y. You can also use Desmos. And what shape would you use to describe the graph? And what happens to the pattern of increase in the long term? So in the long term means as X is getting bigger and bigger and bigger, or in this case, as W is getting bigger and bigger and bigger, what happens to the population of ants? And I'm sure if you think about it, just in the real world situation, what would happen to a population of ants or other creatures as the weeks go on? Okay, so thinking about that and answering this question, what does that shape say about the pattern of increase? So how is it increasing? What is it doing and how is that increasing happening? Okay, so that's your hint for part B. Moving on to a hint for part C. What shape, here's the shape. All right, sorry. So what shape would you use to describe this graph? What happens to the pattern of increase in the long term? So here's an example of this graph, and you can see what it's doing in the long term. Here's your hint for C. So for C, the question is asking, going back, what seems to be the upper limit of the ant population, and how can that limit be found without the graph or calculations, and simply by looking at the equation. So looking back at this graph, we can clearly see that it starts to taper off and it seems to have some sort of upper bound up here. Okay, so that would mean that the ants cannot grow in population so great that they just keep going to infinity and beyond. That's not going to happen. So there's kind of an upper limit to how that growth can occur. So now thinking, how could you, just looking at the equation, think about what that upper limit would be as the number of weeks gets bigger and bigger? And when will the number of ants appear at its limit according to the equation? Okay, so if you're looking at this equation, Okay, as W gets bigger and bigger and bigger, so imagine that that's a very large number, like 1,000,000. You can possibly use a table or possibly just plug in some big numbers until you see what would happen. And using the equation, where would it start to top off, and where would its limit be? We call that, if you want to be fancy, the limit as x approaches infinity of this function p of w. And the question is, what is that limit? What is that sort of boundary on the population of ants? Okay, so there's your hints for question 25. So we're going to move on to question 27 and do a hint for that as well. So question 27 is talking about piecewise defined functions. So a piecewise function is literally what it sounds like. It's a function that's created out of different pieces of functions. And you can see an example of that in problem 11 in the On Your Own. So you can look at that. But here's a table. So it's saying if my taxable income is from 0 to 8,700, then the rule that goes with that is 10% of your income is paid. But if my taxable income is 8,700 to 35,350, then the new rule is 15% of the income over 8,700 plus an extra $870. And you can see the rule for the third tier there. So hint for A is, which category of taxable income did James fall under last year, and how do you know? And hint for B is, which category of taxable income does $20,000 fall under, and how do you know? So basically looking at which of these categories you will fall under for that input, and then using the formulas that's given for that input value, you would plug it into that formula or this formula wherever your input value lies in those different tiers. And that's how you figure out your income tax for that taxable income. Okay, so that's your hint for A and B. Let's look at C and D. So C is a little trickier because you're actually writing your piecewise function. A piecewise function means that you have different function rules over different domains or input values or x values. And the question here says, how many pieces will this one have? Well, there's clearly 3 tiers of taxable income. So this piecewise function will have 3 different pieces or 3 different function formulas. And you need to write an equation for each piece of the domain. So I have an example here because you might not have seen piecewise functions and kind of the symbols we use to represent them. So if you look down here, here's an example of how you would write a piecewise function. So the first example here shows basically an x squared function, but the x squared function is only when x is greater than or equal to -3. So here's -3 right here. If I go greater than that, I have this lovely quadratic function, this lovely parabola that's right here. But if I go less than -3, I have a different function, this linear function that is -x plus 6. Now notice they actually still meet even though they're different functions. So at x equals -3, whether you plug into the first piece of x squared or the second piece of -x plus 6, you're still going to get a value of 9 for that value. So basically they meet there. And that means since they meet there, you have 2 options. If you want x squared to be the definition at x equals -3, then you need to put a little line under the -3 here. Okay. But if you want the other one to be the definition at x equals -3, then you would put a little line under that one. So it really kind of doesn't matter on this particular type of piecewise function because the output is 9 no matter which type of function you choose, no matter if you choose the x squared or the -x plus 6. However, down below, you'll see a different example in how we write the piecewise function. In the different example, we're looking at two functions that don't is if I think that it needs to be defined at x equals -3 for the first function, I would put a solid closed circle on the first function and an open circle on the second function because of the fact that I cannot have two values for -3 in my output at the same time. So notice that if both of these values were part of your equation, this would not be a function because it does not pass the vertical line test, and there are two outputs for one input. So you'd have to put a closed circle on one of these two. So if it were like this and the open circle is on the x squared, or the closed circle is on the x squared and the open circle is on the -x plus 2, then that would mean I'd put the little line under the equation for the closed circle. However, if it was defined the other way around, and I had the open circle on the x squared, and the closed circle on the -x plus 2, then that would mean the little line, meaning -3 is included in this tier, would go there. All right, so that's a little hint. Now you can go back, now that you've seen how you write a piecewise function, and then notice that you use this little like fancy bracket system to show that g of x is equal to both of these pieces depending on the circumstances. And going back to problem number 27, now you should be able to go through and write the piecewise function. Okay. All right. And I'm going to end with a little cartoon for you guys. This poor little vertical line wishes he had a functional relationship. Have a great day. Happy mathing.